Welcome everybody, this is Mr. Ndabezita once again, and this time we are continuing with chemistry. And I'm sorry there's a background noise that is going to disturb us, but I will try to filter that out. So I want to draw your attention to this book, The Introduction to Chemistry Foundation. And this is the 9th edition written by the individual here, and we will be looking at chemical reactions. Just an introduction, and this is the copyright and the publisher of whatever that is to transpire in here. So this is a very good book that is going to give us an insight as to what Chemistry Foundation is all about. So okay, without any further waste of time, let's move to the second slide. I just had a periodic table for you here so that we may know, you may see exactly what is going to happen, but we are not going to deal with a periodic table, so I'm not going to say much on this. I think we will deal with this on some other tutorial. So in section 6.1 we have the evidence for a chemical reaction. What would be the evidence that a chemical reaction has transpired? So they say, what are the clues that a chemical change has taken place? Okay, question mark. So these are some of the things that we can say. We can say that a chemical reaction often gives us a visual signals. So you can have a visual signal that a chemical reaction has taken place, something visual. However, reactions are not always visible. Some of the reactions are not visible. Even if they have occurred, you cannot see this with your naked eye. You have to go to the world of the very small in order to see this. And then we are continuing with some of the clues that a chemical reaction has occurred in table 6.1. We have some of the clues is that there can be a color change, there can be a physical color change that you can see which resembles that a chemical reaction has transpired. There can be a solid that is formed by just looking at the reaction. You can see the solid. If sometimes the reaction can be left for some few minutes, and then sometimes immediately there can be some bubbles that you can see rising up on top of the container as a result of showing that the chemical reaction has transpired. And then lastly, there can be heat or flame is produced. You can hear that something is burning or heat is absorbed in the reaction, speaking about exothermic and endothermic reactions, but we will deal with that. So these are just basically the four reasons or clues that a chemical reaction has taken place. There can be a color change, there's a solid that is formed, bubbles formed, there can be heat or flame that is produced, or the heat that is absorbed. Okay, we continue in this and we have an exercise, which is exercise 1. They say that we should identify a clue that indicates a reaction has occurred in the given image. So we have an image that we need to analyze. We have a beaker or a container. There's a battery inside here, and this battery is inside, I don't know whether I can say this is water or something, I'm not very sure. But what I can tell is that we have oxygen gas coming out on one side and hydrogen gas coming out on the other side. Okay, both from the battery as being indicated, and there's water inside, so we have some bubbles of hydrogen gas there. Now, one thing most important that we need to see here, just as we learned in the previous study, is that this is a molecule of oxygen gas, and we know that gases will rise up to fill up the container in which they are inside, and the forces between them are very weak because the bonds have been broken and they are incredibly away from one another, and they will bounce on the walls of the container. Just as we see that these are some of the characteristics of a gas that we looked at in the previous tutorial. So what could be, if you are asked, What clue is there that might show us that there has been a chemical reaction in here? Please just see that this is just a beaker that is inside of water. I think there's water inside of this beaker, and then we have just this blue shape outside here, and this is just a reflection of the blue color that is reflected inside here. Please, there's plain water here and we're just seeing the bubbles. This is not a sign of there's a color change. This is just a reflection of the blue color, as you can see there. So what could be a clue that might give us an insight that there's a chemical reaction that has happened here or that is happening currently? Is there any color changes? No, as we have said. Are there any solid that is formed? There's no solid that is formed. Are there bubbles present? Yes, the hydrogen gas is there for us. And is there a flame that is produced? No. So a clue that might give us an insight that a chemical reaction has transpired in here are the bubbles that are present. Very important that we okay, we can continue in our study. So let me just do this. Very good. So we see that there are bubbles present as a sign that a chemical reaction has transpired. Okay, that is fine. Let me just do this. Very good. Now we move to exercise 2. They say to us we should identify a clue that indicates a reaction has occurred in the statement and in the given image. So an image is provided before us. Here they are, 3 images. Let's just read what is happening here. Colorless hydrochloric acid is added to a red solution of cobalt 2 nitrate, turning the solution blue. So we are adding hydrochloric acid, the drops of hydrochloric acid inside a solution of cobalt 2 nitrate. And before we do this, the color was red. And as we keep on adding more drops and more drops, the color rapidly changes from red to blue. So what is a reason for that? We will deal with that at a later stage, but we can see that there's a color change, and immediately when we identify a color change, that tells us there's a chemical reaction happening in here. And the more you add this hydrochloric acid, the stronger the blue color will come, will be present, because with just a few drops, remember, they will slowly change the color red, and with more drops it will take over the red color and turn permanently to blue. And as you keep on adding that, the stronger the blue color will come. So a change in color has shown us that there's a chemical reaction taking place here. And remember, this chemical reaction that is taking place, we cannot see it with our own eyes. We're just seeing the color changes, but we cannot tell clearly and purely exactly what is happening in the world of the very small. But we will also deal with that some other time. Now we are in exercise 3, and in exercise 3 we read that identify a clue that indicates that a reaction has occurred in the statement and in the given image. A solid forms when a solution of sodium dichromate is added to a solution of lead nitrate. Before we look at that, it is so important that I also stress the fact that here, not in every chemical reaction the opposite is true. We are adding the drops of hydrochloric acid inside of cobalt 2 nitrate in here. In some other reactions, if not this one, the reverse is impossible. You cannot add the drops of cobalt nitrate inside of hydrochloric acid. That might cause a catastrophe. Please, it is very important that we note that. It is important because in chemistry we are dealing with order. We are adding hydrochloric acid inside of cobalt 2 nitrate, not the drops of carbon nitrate inside of hydrochloric acid. But we will deal with the reason why that should be and why that should not be in the reverse if it is true in this case. Okay, so here what is happening? A solid forms when a solution of sodium dichromate is added to a solution of lead nitrate. So we have lead nitrate as a colorless substance, as we see there, and we are adding sodium dichromate, which is a yellow inside here. And then what is going to happen here? We are forming a solid. You will not see a gas that is formed. There are no bubbles present. A flame is not produced. You will just see a solid that is forming if this reaction is left to cool down after some time. You will see that there is a solid that is formed in here. Again, it is very important that we stress that sodium dichromate should be added inside of lead nitrate. So we will investigate whether the opposite is true, as to say, can we add lead nitrate inside of sodium dichromate? The reverse, whether this will not cause any problems, but we will deal with that some other time as well. So that is fine. We have thus far saw that some of the reactions that we looked at, they can be able to tell us that there is a chemical reaction by the presence of the bubbles. On the second one, there can be a color change, and on this one there's a solid that can be formed. So we can see that. And we haven't yet dealt with a reaction where a flame is produced, but that's fine. Let's continue in this. Now in 6.2, now we are looking at chemical equations. From mathematics, the left hand side has to be equals to the right hand side. Okay, that is fine. A chemical reaction involves changing the ways in which atoms in the compound are grouped. Okay, let me just do this just to check whether the recording is going on. Let me check what is happening here. Okay, everything is still happening the way it should. Right. So let me just do this. I just want to place this here, guys, just to keep track of time. Okay, let me just leave it there. So let's go back to our slide. So here we are with chemical reactions. Okay, let me just do this very fast. All right. Chemical reactions involve changing the ways in which the atoms in a compound are grouped. Okay, that is fine. So one most important thing to note here is that chemical reactions involve the changing of the ways in which the atoms are grouped in a compound. So very important. You can start first with a reaction in this way. You have on one beaker methane and on another beaker oxygen, and when the two are allowed to react in the presence of heat, you will have carbon dioxide plus water. So there's a regrouping that has happened. As you can see, you had CH4, now you have C with oxygen. C was with hydrogen, it's no longer with hydrogen as a product, it's now with oxygen. And oxygen was a diatomic molecule on its own, it's now with hydrogen. So there's a regrouping that is transpired. A chemical equation represents a chemical reaction. So when you are looking at a chemical equation, you are in actual fact looking at a chemical reaction. This is exactly what we need to understand. Reactants are shown on the left of the arrow. There they are. We have the reactants, and on the right of the arrow we have the products. So this is methane, highly flammable, and it will burn in the presence of oxygen when heated, and it will produce carbon dioxide plus water. Very important. Okay, let me just do this. Let's go to the next slide. Chemical reactions continued. In a chemical reactions, atoms are neither created nor destroyed. Now, here we are in a chemical reaction because we are looking at the chemical equations which we said in actual fact represent a chemical reaction. So we are therefore saying there, in a chemical reactions, atoms are neither created nor destroyed. In this chemical reaction, there's nothing, atoms are not created here. We are not creating new atoms. We are simply allowing the atoms to react with one another the way in which they feel that they should. Very important that we note that. The atoms will react with the members that they feel like reacting with. You can never and ever force oxygen to react with something that it doesn't want to react with. The reason that we have methane that burns in the presence of oxygen forming carbon dioxide and water, it's because methane, when it reacts with oxygen, it wants to produce that. You are not the one telling the reaction what to produce. The reaction will tell you exactly what the outcome would be. You would just only prepare the necessary preparations for that to transpire. It's like taking a pill to the body. You are not in any way curing the body by inserting a pill inside of the body. You are creating circumstances that allows the body to react the way it must and the way it should when the pill is inside. Exactly the same thing is happening with these atoms. These atoms will react with the members that they feel that they should react, and they will produce that which they want to produce, not you being the one telling whether methane can react with hydrochloric acid or not. If that reaction is impossible, it simply means that the two cannot react with one another, and irrespective of whether you like it or not, the reaction will not take place. It is very important that we note that a chemical reaction, it's not man driven, it is nature driven. But man can allow the circumstances that can allow nature to react the way in which it wants. Very important. Therefore, we are saying in a chemical reaction, atoms are neither created nor destroyed. In a chemical reaction, we are not creating atoms. We are creating a new product because the atoms reacted the way in which they want in order to form a new substance. So old bonds are broken and new bonds are made with something totally different from before. Highly important that you note these little comments that I'm trying to make here. So much important that you understand this. Okay, so during a chemical reaction, we are not forming new atoms. We are not destroying anything here. We are simply forming a product, something completely different from what you had initially. So this is like a machine. So when you have this, the machine, which are the conditions that you are setting for the two, shall give you something totally different on the other side. In a chemical reactions, atoms are neither created nor destroyed. All atoms present in the reactant must be accounted for among the product. Now, what are we saying by that? If you had one carbon before the reaction, you must have one carbon after the reaction. If you had 4 hydrogens before the reaction, You see, you have 4. After the reaction, you have 2 because we have not balanced the equation. Please be careful here. The equation is not balanced here. If we balance this, then you will have a 2 here that will give you exactly 4. Because remember, we said atoms are not created nor destroyed. So this, because it is not balanced, it appears as if we destroyed 2 hydrogens. No. Remember, when we balance this, everything will be in order. Very important. Let's continue in this. There must be the same number of each type of an atom on both sides of the arrow. So each type of an atom, 1 carbon, 1 carbon. Hydrogen 4, there must be hydrogen 4. 2 oxygens, there must be 2 oxygens on a product. But when you balance this, you might want to modify some things. But we will deal with that when we get there. Right, okay, that is fine. We can continue in this balancing a chemical equation now. Now we are dealing with the balancing, because during a chemical reactions, atoms cannot be created or be destroyed, but they can be transformed into something totally different. But the individual atoms that are reacting should always be the same on the left and on the right. So when we balance a chemical reaction, I'm not going to use this. It's a little bit confusing for me. I want us to come here. Now remember initially what we had. We had CH4, O2, CO2, H2O. So we had CH4, O2, CO2, H2O. Now remember, we have 1. Now this is a balanced chemical equation. This is a balanced reaction, chemical reaction. This is how a reaction will take place. Without you ensuring that the number of moles are the same, this reaction will never transpire. Very important. So you have 1 carbon, 4 hydrogens, 4 oxygens, 2 plus 2, it's 4. So the reaction will transpire. Very important that we understand the balancing here. Okay, that is fine. Let's now look at the physical state. Physical state of a compound are often given in a chemical symbol, the state in which before they can react. Unfortunately, here we did not show the states of all this, but we will see them as we continue. So we have the symbology that we use for a solid as liquid and gas. An aqueous solution, something that dissolves in water, is an aqueous solution. So okay, that is fine, and here we are trying to address that. So when potassium, which is a solid, there it is, potassium, reacts with water, that is a liquid state in here, this will give you hydrogen gas and potassium hydroxide. Very important. And potassium hydroxide is an aqueous solution. As a product, and hydrogen gas comes as a product as well. There will be some bubbles here. Let's just try to look initially first. So first of all, we have liquid H2O, and we insert some chunks of potassium inside here. We leave this for a few seconds. What is going to happen there, you will have hydrogen gas here at the bubbles plus potassium hydroxide as the product. So we understand that. So these are just the phases, the states, physical state of the substances. So this is a physical substance. You can see that it's a potassium solid, liquid, physical state. You allow them to react for some time, and then you will see that you will get these bubbles as a sign of hydrogen gas and potassium hydroxide as an aqueous solution dissolving inside of water. Okay, that is fine. We have understood. When blue light shines on a mixture of hydrogen gas and chlorine gas, the element reacts explosively to form gaseous hydrochloric acid. What is the unbalanced equation for this process? Now they are asking me, now I am in so much trouble. So they say when blue light shines on a mixture of hydrogen gas and chlorine gas, so we have hydrogen gas that and chlorine gas, and we allow a blue light to shine on this mixture. Very important that we understand that. So hydrogen gas plus chlorine gas, because they are both gases. Blue light shines on a mixture of hydrogen gas and chlorine gas. The elements react explosively to form a gaseous hydrochloric acid. So hydrochloric acid is a product and it is a gas. Very important. So the product is a hydrochloric acid. So by just looking in here, okay, there's a product, hydrochloric acid, good. This one, the product is hydrogen gas plus this is totally out, hydrochloric as a gas, totally out. Sorry, this one and that one are quite possible. Now let's look at what the question is saying. What is the unbalanced equation for this process? What is the unbalanced? Alright, we know that hydrogen gas occurs as a diatomic molecule. So hydrogen gas reacts with the chlorine gas. Now let me take you back to the periodic table. So we have hydrogen that reacts with a chlorine gas. Let's go and look at chlorine. So chlorine, it's in group 17. It has a valency of 1. Let me just take you through something just to give you some more information on chlorine. So chlorine, it's a halogen, first of all, very important, and it is a halogen, very highly dangerous. So chlorine is a chemical element with symbols Cl and atomic number of 17. It has a relative atomic mass of 35.5. We can see that, okay, where it's my this, there it is. Chlorine is in the group of halogens, group 17, and it is the second lightest halogen following fluorine. Okay, that is fine. So one thing that we need to note here is that it has a valency of how much? It has a valency of 1, and the ion, it's Cl minus. So let's just check very fast the valency of this chlorine. It has a valency of 1. So I just wanted to check that for you. Okay, it is not mentioned in here, but we know that it has a valency of 1. Okay, that is fine. Let's continue in this. So one thing worthy of noting here is that chlorine is more electronegative than hydrogen. So hydrogen has a plus ion and chlorine has a minus ion because it is more electronegative. So when the reaction happens between chlorine and hydrogen, chlorine tends to pull the electron to itself because it is more electronegative. We will deal with that when time is right. But let's go back very quickly just to answer the question. So they say to us here, what is the unbalanced equation for this process? So hydrogen reacts with methane. This is totally out. The reaction is between hydrogen and chlorine. Hydrochloric acid forms, okay, totally out. This is also totally out. The only correct one is this one. Hydrogen gas reacts with the chlorine gas to form hydrochloric acid or hydrogen chloride. So one most important thing that we need to note here, the ratio here is 1:1 because I've shown you in here. That's why the equation is written as HCl. It donates 1 electron, it accepts 1 electron. because it has a valency. It has a space of only accepting 1. It has a space of also donating 1. So when the reaction happens, it's in the ratio 1:1. Hence, we have the formula as HCl. HCl. Very important that we note that. Okay, we continue writing a balanced equation for a chemical reaction. The principle that lies at the heart of balancing the process is that atoms are conserved in a chemical reaction. That is just to say, the atoms before the reaction has to be equals to the atoms after the reaction. Conservation of atoms. Atoms are neither created nor destroyed. The same number of each type of an atom is found among the reactants and among the products. We looked at that. Chemists determine the identity of the reactants and the products of a reaction by experimental observations. The identities or formulas of the compounds must never be changed when balancing a chemical equation. Let's try to read that with care. The identities or the formulas for the compounds must never be changed when balancing a chemical equation. When you balance a chemical equation here, you do not write this the way in which you want. You want to take HCl to this side, take chlorine to that side. Please, we are not in mathematical literacy here. Please, as a belief, you don't do that. The orientation and the way in which things are written here, the reactants becomes reactants and a product is a product. As a belief, please, we are not in a history class here. Okay, let's continue. So we understand that exactly what it means. We understand that. Right. Now let's go to how to write a balanced equation. Read the description of the chemical reaction. First of all, identify the reactants, the products and their states, liquid, solid or gas, aqueous, solution and so on. Write the appropriate formulas. Hydrogen gas and oxygen gas combine to form liquid water or H2O. Write the unbalanced equation that summarizes the information of the previous step. So hydrogen gas, because we are told hydrogen gas reacts with oxygen gas to form liquid water. And now you proceed to balance here. You have 2 hydrogens before the reactions. There it is. You have 2 oxygens before the reaction. You have only 1. There's a problem. You have to bring in a 2 here. When you bring in a 2 here, now you have 4 hydrogens. You'll have to bring in a 2 there. Very important. And here we are trying to balance there. So here we have 2 oxygen atoms, 2 oxygen, 4 hydrogen. 2 times 2 is 4. Or could be, they say preferred could be, we can have 8. If you decide to replace this 2 with 4, we can have 8 hydrogens and 4 oxygens. So when it comes here, you'll have 4 times 2, which is 8 hydrogens and 4 oxygens. Preferred or could be in that way. But remember, when you do it in this way, the number of moles are not the same here. One worthy point to note: the number of moles, the ratio of moles are not the same. Right. Balance the following equation in a standard form or the lowest multiple integers. So this is the lowest multiple integer and the high multiple integer values. So we are using integers to balance a chemical equation. At the end of the day, you must have an integer. Okay, balance the following equation in a standard form or the lowest multiple integers and determine the sum of the coefficients. Okay, that is fine. So we have iron oxide plus oxygen gas giving you that. as a solid. Now let's check what is happening here. So we have 1 ion Fe, we have 2. There's a problem here, very important, so we will have to put in a 2 here. So when we put in a 2 here, we now have 2 oxygens plus 2 oxygens, which is 4, and on the right we have a 3. That's highly problematic. So if I have a 3 here, it simply tells me that go and balance this side before you can balance that side. So in order to balance oxygen here, let me put a 2 here so that I have a 6. Remember, I need to have an integer at the end of the day. So I will put 2 here to have 2 times 3, which is 6 oxygens. Now that I have 6 oxygens, I need to balance this side. I have 1 and 2, which is 3. I want to have 6. And if I put a 2 here, I will have 2 plus 2, which is 4. And when I put a 2 here, I will have 4 plus 2, which is 6. And when I put a 2 here, I can put a 2 there, then it is balanced. Very, very balanced. So you will have 2, 2, and 2. Sorry, not 2. Remember, if I put a 2 here, I will have a 4. So if I have a 4 here, let me put a 4 here. So I will have 4 Fe and 4 Fe. I wish I have written this on a paper, but that's fine. So let's put a 4 here so that we have a 4 here and 2 times 2, which is 4 there. Fe is balanced. But when I put a 4 here, I have a 4 oxygen plus 2, which is 6. Now I have a 6 here. And when I have a 6 here, I can put a 2 there. And I will have a 4 and a 6. So it is balanced. So you put in a 4 here and you put in a 2 there. And then they say the sum of the coefficients. So you have 4 plus 1, which is 5, plus 2, which is 7. So 4 plus 1 is 5, 5 plus 2 is 7. So the correct answer is 7. Okay, that is fine. Let me just do this very quickly. The computer is turning off. Okay guys, let me just break it here and I will edit this video when we are done. Or let me just quickly insert a charger. I can just eliminate this problem by just quickly inserting in a charger. And there we are. Alright, so let's continue in this chemistry stuff. So let me just do this. So which of the following equations correctly balance the chemical equation given below? There may be more than one correct balanced equation. If a balanced equation is incorrect, explain what is incorrect about it. Let me just take you back in this. Let me just take you back. Was it here? Yes. They said check to see that the coefficients used are the smallest integers that give the balanced equation. So we can use the smallest integers or a little bit more higher integers. So there can be more than one correct solution for that. So let's go here.